Welcome, everyone. Let's relax a little bit and from the election stress and enjoy some beautiful science. Today we are privileged to have with us Professor Cristina Marchetti. She's a really distinguished theoretical physicist who worked on a broad range of problems in condensed matter and biological physics. After 30 years at Syracuse University, she has finally joined us in the University of California system at Santa Barbara, however. And she has, in 2018, since then, she has been a member of the physics department there. So in her research journey, she explored a really wide range of topics, including supercooled fluids, superconductors, driven disordered systems, and the mechanics of biological tissues. But her current focus, I would say ongoing for a decade now perhaps, is on the fascinating world of active matter. And this is really a field she has helped pioneered. So active matter explores systems that consist of particles or entities that consume energy to move around and to generate their own forces. And this very fact of local energy injection makes all the difference. It generates a wealth of collective phenomena that are unfamiliar from regular statistical physics, which is constrained to obey detailed balance. So one observes new types of phases and phase transitions, which are really useful in describing real-world phenomena like collective migration of birds or the behavior of human crowds, as well as cells in the process of wound healing. And these phenomena may also be used in the future to be exploited in smart metamaterials. And so Professor Marchetti was not only key in discovering a good fraction of those phenomena, but she really showed us how soft matter and statistical physics need to be extended to describe these phenomena theoretically using fields on large lengths and time scales. And you know, her influential work was recognized by numerous awards. I won't mention all of them, but let me just mention that she's a member of the American Academy of Arts and Sciences, of the National Academy of Sciences, and in 2019 she received the Leo Kardanov Prize from the APS. So please join me in welcoming Professor Marchetti as she guides us through the emergent behaviors of active and living matter.
Thank you, Oscar, for that very kind introduction. And it's a pleasure to be here and an honor. I had many interesting conversations today. And actually, I was telling, I think, David Limmer that my life could have been different if a million years ago I was actually offered a postdoctoral position here with David Chandler. I did not come at that time because I was honestly worried about the cost of living in California, in Berkeley in particular. But I've always kind of had a little bit of a regret in the back of my life. Anyway, it's really a wonderful place to be with a lot going on and just a beautiful crowd here. So as Oscar said, I want to tell you about this field that has become very popular. He already actually told you what the field is all about. Maybe I should skip my introduction. But it is this field of antimatter. And I thought I would start with a little bit of a historical introduction. I haven't personally worked on bird flocking, to be clear. But this field really started in 1995, and it would be unfair to start talking antimatter without showing you an example of bird flocking, because it did start with the idea that physicists actually wanted to use statistical physics to describe bird flocking. So here we go. What is this is these sort of birds that form, starlings, that form these large sort of like soft objects that bend and fold in the sky like a fluid. And so the idea was, well, you know, physics had great success in understanding how through interactions, atoms and molecules form material with behavior very different from those of the individual constituents. can we use similar ideas to describe phenomena like these? These are also emergent phenomena, collective organization. And by the way, please do interrupt me with questions during the talk. It makes it actually much better, so please feel free to do that. So back in 1995, Tamas Vicek, essentially inspired by the physics of magnetism, introduced this model, which we now know as the Vicek model, where essentially it was introduced in 2 dimensions. And so he said a bird is sort of like an XY spin, only it's a flying spin. The spin represents the bird. He flies with a speed v0, which is fixed. And it changes its direction, denoted by an angle, through alignment with the neighbors within a certain range, plus some noise. And this was a model that he simulated on the computer. The order parameter is the mean velocity. For large noise or low density, the mean velocity is 0. At high, what did I say? I say it right, maybe I said it wrong. For low noise and high density, the mean velocity is non-zero. That is, the birds on average are moving in the same direction. That is a flock. Now, to be fair, I also have here another picture, which is the picture of Craig Reynolds, a computer scientist working for the animation industry, who actually has essentially developed the same model quite a few years earlier and used it in many movies, such as Batman Returns. Reynolds actually won a few Oscars for his work. But what Vicek did, that at least to us physicists resonates with us, was that he was the first one who really put this model in the framework of phase transitions, introduced this as a phase transition. So if you take the Vicek model and you simulate it on a computer, you get flocks. The color here is the direction in which the birds are moving, the direction of motion. And for a long time, well, Vicek thought this would be a continuous phase transition, and it took actually quite a long time, like 20 years, and a lot of theoretical work, a lot of simulations to conclude that actually the transition is first order. The disordered state is a gas, the ordered state is a liquid, and there is a region of coexistence where you get ordered region through the disordered gas, and the structure of the ordered regions actually depends on the geometry of your simulations. So the lesson we learned from Vicek is that this type of collective motion can be described as a phase transition, and really provided a new paradigm for describing what we call active systems and also living systems. So today, what we call active matter is, as kind of Oscar already said, any collections of active particles, and active particles themselves, if you like, are engines. They consume energy from the environment to generate their own motion and forces. So we have, through interactions, they organize in collective dynamical states at large scales. And we have examples on many, many scales, from a protein that drive the organization inside living cells, these are cell divisions driven by microtubules, to engineered active particles, synthetic microswimmers, bacteria, eukaryotic cells, robots, and even on lower scales. The ideas and the formalism of active matter physics has been used to describe even the behavior of human crowds. So in all these examples, you have energy input at the particle level that cascades to large scale to give you this dynamics and organization. Now, what I want to do today is basically give you a couple of specific examples of this new kind of non-equilibrium matter, which is made not of atoms and molecules, but if you like, of engines that generate their own motion and forces, and ask the kind of questions we like to ask in physics, such as what new kind of states are possible. One question that is interesting in this context is, what are the parameters that tune the change from one state to the other? In equilibrium offers temperature or density. Here, density is possibly one, but generally not temperature. And for instance, the propulsion speed may be one of these parameters that actually tune the phase transition. So the motility, for instance, of cells or bacteria. Can we classify the behaviors and identify generic properties and maybe identify some universality classes of active systems? And there has been quite a lot of progress in these directions. In particular, we classify systems according to their symmetry of the constituents, if you like. So spherical bacteria that are swimmers, are self-propelled, or spherical colloids, which you can make in a lab that are self-propelled, provide an example of what we call scalar active matter. Here, the order parameter is just the density that might quantify how this quantity aggregate or not, these particles aggregate or not. Birds or fish or some bacteria provide examples of ferromagnetic or polar active matter. They swim, they have a head and a tail, and they may organize in state with essentially ferromagnetic order. But there are also many examples, and actually many more, it turns out, than we had first thought, of active particles that don't have a head in the tail. There are cells that kind of move back and forth, like the melanocytes to shake around the pigment in your skin. So they go nowhere on average, but yet are active because they exert force dipoles on their environment, and they organize then in states with nematic orientational order. And I plan to specifically give you, tell you a little bit about the behavior of the scalar kind and the nematic type in this talk. Of course, the bird flocking is the middle one, but I will not tell you anything more about it. So, first question that comes up is, okay, so why is active matter different from anything that is driven out of equilibrium by, say, driving at the boundary, like in this Rayleigh-Bernard convection between hot and cold plates, or by an external force like gravity or electric field? What actually makes it different? And to understand that, we need to go back and think about sort of the simplest non-equilibrium statistical physics problem, which is Brownian motion. We don't do all that well in our classes at teaching non-equilibrium statistical physics. Sometimes you don't even cover Brownian motion, so let me actually go through it. So what is Brownian motion? Well, it's the famous random jiggling of, say, the grain of pollen in water or dust of particles in air. And so how do we describe it? So we have let's say, a spherical particle in a fluid which is in equilibrium. And one way for describing this kind of dynamics is through essentially a stochastic version of Newton's law that equates the mass times acceleration to the forces experienced by the particle. And we can split these forces due to the surrounding fluid into parts, the mean drag, and sort of the random kicks that the fluid molecule exert on this particle, which enter here as noise. This eta is a Gaussian random force with unit variance. Now, in most cases, if we are interested in a colloidal particle, maybe a micron in size, the time scale of relaxation of the velocity is so short that effectively we can neglect inertia. So instead of Newton's law, we have what is called over-damped dynamics, which is really just force balance. So let's look at that simple case. So we just balance drag to random kicks, and say we calculate the mean square displacement. Of course, these particles go nowhere on average, but we calculate the mean square displacement, which should be diffusing at all time. And the diffusion coefficient is just kT divided by the drag. That's famous Einstein relation, goes back to 1905. Now, why there is this relationship between the dissipation and the diffusion? And this is simply because the solvent in this case, which is in equilibrium, yields both the drag and these driving forces, which you can show must have a strength proportional to kT if you want this system to relax to thermal equilibrium at long times. In other words, there is detailed balance. The rates of forward and reverse processes must be balanced, or another way to say is that fluctuation dissipation theorem applies, and in fact, Einstein relation, if you like, is the simplest example of a fluctuation dissipation theorem. But if you look at a bacterium swimming in a fluid, how is it different? Well, of course, we have the drag. We have the random kicks by the fluid molecule, still both coming from the fluid. But then, the random kicks drives the Brownian motion. But in addition, there is an internally generated drive that I will call the cell propulsion. And generally, this greatly exceeds the thermal drive from collisions with the fluid molecules. So because of this, there is no balance between drive and dissipation. There is no detailed balance, no time reversal symmetry for the dynamics of this cell-propelled particle, as I might call it. And in addition, this breaking of time reversal symmetry, unlike the situation where you may have charged particles driven by an electric field, of course, this also breaks time reversal symmetry, but it does so globally, the same on every particle. Here, this TRS breaking is actually local, and the result is that, as we will see, while the dynamic of one particle may not be terribly interesting, when you have interaction, a bunch of new phenomena can actually arise. And in particular, quite some time ago, we looked at this sort of simplest model, which has now become known as active Brownian particle, which is, again, a colloid with over-damped dynamics, so we don't have any inertia here. And for whatever reason, it has a propulsive force, so it swims at this speed v0, and the direction in which it swims is randomized by, at a rate 1 over tau, so this polarization axis, or motility, has, this is in 2 dimensions, is described by an angle theta, and the angle theta itself undergoes diffusion at a rate 1 over tau. This tau, you could call it the persistence time. So essentially, this particle is not quite a Brownian particle. It travels in a straight line for a time tau, or a length scale LP, V0 times tau, and then the direction in which it travels is randomized by rotational noise. Now, this actually has been realized by the group of Paul Chekin at NYU by essentially embedding a piece of hematite in a plastic bead of size about a micron. So hematite, and then immersing this colloid in a suspension that contains hydrogen peroxide. Hematite can catalyze the breakdown of hydrogen peroxide into oxygen and water, but only if you shine UV light on it. And so I'm going to show you this video, and what you will see is when there is no light, these colloids are just jiggling around. They undergo Brownian motion. But when there is light, they swim, and they become swimmer. And they actually swim at speeds pretty much comparable to speeds at which E. coli might actually swim, which is very fast. E. coli has a body of few angstrom. This is few micron. This is 15 micron per second. So let's see that. So now the light is off. They're just jiggling, Brownian motion. But when the light is on, they swim. In this directed way, they perform a persistent random walk. Okay? So, all right, well, my equation is really simple. I can calculate the mean square displacement. And if I do that, I find, perhaps disappointingly, that at a long time, the dynamics is still diffusing. It's really just the square of the step, which is the persistence length, divided by the persistent time. That's the diffusion coefficient. So I would then be tempted to say that these active particles are just kind of hot colloids. I can define an effective temperature by equating this by using Einstein relation. And if I calculate this effective temperature, I will find it to be about 100 times bigger than the actual temperature. But still, dynamics is relatively boring. This is true if I just have one particle. But if I have many interacting ones with just repulsive interactions, these are just, say, hard spheres, so, or softer, any kind of repulsion, as a matter of fact. So that's the repulsive, that's the interaction. What I find is that these particles spontaneously phase separate into a dense phase surrounded by an active gas. Now, in equilibrium, we need attractive forces for a liquid for a gas to condense into a liquid. Phase separation requires attraction. Here, there is just repulsion, and yet they undergo phase separation. So this phenomenon has been called motility-induced phase separation, and has been described theoretically in a very sophisticated way, but you can kind of understand it rather simply through an argument actually due to the group of Aparna Bhaskaran a few years ago, as essentially arising from the lack of detail balance, the sense that the flux in is different from the flux out. So if you actually have a cluster of the cell-propelled particles, the flux in would be proportional to the density of gas particle times their speed. But the flux out is essentially controlled by the persistence time, because in order to escape, first of all, these particles have to rotate their nose in the right direction. Another way to say is that this condensation happens very simplistically because if I hit other particles, or a wall for that matter, and the persistence time is long enough, I don't have time to turn my nose away before other particles come in. And in fact, you can get an estimate for the phase separation, simply equating the persistence time to the mean free time between collisions. And at a little bit, going a sort of a more mean field theory type description. So this phenomenon, now known as motility-induced phase separation, very nice name, proposed by Marchetti quite some years ago, has been seen in large-scale simulation in 2 and 3 dimensions with all kinds of repulsive interactions, soft and hard. And there's actually been developed a quite careful effective field theory derived by coarse-graining the microscopic dynamics. So it's actually a generic phenomenon that underlies much of the aggregation seen in bacteria in the living world. So, for instance, of course, a gas fills the container. An active gas does not fill the container, accumulates on the walls. So it's really contrary to our intuition. And essentially what you can do, you can derive a sort of a Zvoluchovsky or Fokker-Planck equation, whether you call it one or the other. It's a bit of a, anyway, for the probability of finding a particle at position r with orientation theta at time t. And this is the divergence of some flux that is given by the cell propulsion. And of course, a contribution from the repulsive forces. Essentially, you can calculate this term for a specific form of cell propulsion. And you can see that if you project this mean force in the direction of polarization of the particle along n hat, that contribution from this mean force will give you a correction to the propulsion speed that depends on density. And if the interactions are repulsive, it tends to lower the propulsion speed. And it is this suppression of motility due to crowding that essentially drives this phenomenon. In fact, you can go one step further. You can actually take an angular moment of this equation and rewrite it as a nonlinear diffusion equation, where the diffusion coefficient can be calculated in terms of this density dependence propulsion speed, and there will be a range of densities and persistence times where this diffusion coefficient goes negative. And essentially what you get in this mean field in this mean field description is essentially a spinodal instability, if you're familiar with that, where you have density fluctuations that instead of decaying, grow, and the system spontaneously aggregates. It's essentially self-trapping. In equilibrium, if you have density inhomogeneities, then they diffuse, and the long-time solution is that the density is constant everywhere. In this system, if you have a density inhomogeneities, density builds up due to essentially self-trapping. You can actually find a steady-state solution of this equation, which is that the density goes like 1 over the cell propulsion speed, and that itself depends on density. As particles crowd, cell propulsion goes down, density goes up, and there is a feedback that drives this instability. A slightly more perhaps technical way is you can also show that these equations can be mapped exactly on what's called the Cahn-Hilliard or 5-4 theory, which is a standard theory of equilibrium phase separation, where you have effectively a negative diffusion coefficient, which I've chosen as -1 here, cubic term in the density that stabilizes the instability, and the term that controls interfacial tension. This is, the black part will be your mean field description. There are then actually explicitly terms that break time reversal symmetry and can affect the details of the, for instance, the kinetics of the phase separation and so on, but they don't really affect the mean field phase diagram. And a lot of work has been done on this, especially by the group of Mike Cates, now in Cambridge. I just was going to show you a couple of examples here. So essentially, the message here is that active particles always accumulate when they slow down, something phenomenon familiar to anybody who has been on bumper cars. These are, again, my light-activated colloids, now at a higher density. And what you're going to see is when then the light is on, they aggregate into this kind of crystal. They're sedimented at the bottom of the container, and they aggregate into this kind of 2D crystal. And when the light goes off, the crystals form apart because the motility is what drives the aggregation here. And this other video is kind of a fun example from Alberto Fernandez Nieves, who works with ants. And just a few years ago, he had this article on motility-induced phase separation in fire ants. Of course, there's a lot of other stuff at play here, but I just thought it was kind of a, so this notion of motility-induced phase separation has been used across in many systems. Now, to be clear, the simplest model I showed you, these self-propelled particles, always predicts what we call bulk phase separation, meaning half of the system becomes, say, a dense liquid, half of the system is gas. In nature, actually, most of the time, you see final size clusters. And the mechanisms that pick up the length scale that controls the size of the cluster have been studied a lot and can be many. Birth and death can do that. Various types of chemotaxis can do that. Probably in the ants, there are some other biochemical signaling or that controls that. So those are not generic phenomena. The generic phenomenon would be the bulk phase separation. Let's see, trying to think. Okay, what am I doing? Okay, so anyway, so the message that I wanted to leave you is that this motility-induced phase separation does provide a unified framework for understanding a lot of the condensation, organization, aggregation that you see in both synthetic and living active systems. Now, there is a very interesting thing that comes up that I've been working on recently is when you actually consider a mixture of active and passive particles. Then you can actually show that you get interactions that we call non-reciprocal in the sense that seemingly evade Newton's third law. Newton's third law of action-reaction says that for every action there is an equal and opposite reaction. But in these systems, if you had this kind of a mixture, and in many other examples, what you can find is that the effective, of course, the interactions at the microscopic levels, Newton's is okay, they're still reciprocal, but the effective interactions actually become non-reciprocal. And we've been working on the following kind of example. So as I just told you, I have these active particles, say I have a density rho A of them, and their dynamics can be captured by this Cahn-Hilliard equation with a negative diffusion coefficient, a cubic term, and a tension term. And they undergo phase separation. Now let's mix them up with the density rho P of regular passive Brownian particles. Then I will have two coupled diffusion type equations for the density of active and the density of passive particles. The passive particles are just diffusing, but I also have cross-diffusive coupling, okay? Now, the active particles have this negative active-active diffusion coefficient, and they can actually phase separate. But in addition, their dynamics, the dynamics of the active particle is slowed down by collisions with both active and passive particles. And you can show through coarse graining that the cross-diffusion DAP can also be driven negative in a range of densities or relative concentrations. On the other hand, the passive particles are just regular Brownian particles, and so both this diffusion coefficient in the second equations are positive. So you have an example here of diffusion type, sorry, Canillard equation coupled to diffusion, where the cross-diffusion coefficient can be antagonistic, of opposite sign, providing a type of chase and run dynamics like in prey-predator model, although for conserved fields that you normally expect to decay, not to do anything more interesting than that, as a matter of fact. And if you simulate this kind of mixture of particles, what you find, indeed, is fact my phase-separated patterns become traveling that can be set into motion. And it turns out this is actually a generic feature of this so-called non-reciprocal interaction that can actually turn, say, a pattern into a traveling pattern actually, I'm going to show you something. So these were actually pretty large-scale simulations that were done by my students from IS Shocker a few years ago. So it turns out, and this is an example of a system where this non-reciprocity, if you like, is emergent in the sense that it's not there at the micro scale, but it emerges upon coarse training. And this is an area, this idea of considering non-reciprocal interactions which are actually kind of always there where the system interactions are mediated by a non-equilibrium system, is become very active fields of research, and it's been shown that non-reciprocity provides a generic mechanism for time-dependent phases. So in the case I showed you, where you have two fields that before they were called rho A and rho P, here they're called phi and psi, but let's say they're the same thing. So you have two fields that undergo phase separation. Once you couple them non-reciprocally, you get traveling waves. The group of Vincenzo Vitelli at Chicago has considered two Vichek-type models, or flocking models, coupled non-reciprocally in the sense that maybe the blue wants to ride with the red, but the red wants to anti-line with the blue. And then what you get is that a chiral state, so the original system with reciprocal interaction as polar order. When you couple them non-reciprocally, you get a chiral state where essentially these birds chase each other's tail. And in general, there are, of course, many examples of traveling pattern in biology that can be modeled in a similar way through this kind of chase and run or activator-inhibitor coupling, where a protein may recruit another protein that then detaches the first one. These are traveling wave of a protein on the membrane of a starfish embryo in experiments done by Nick Tafakri at MIT. In the context of my active and passive particles, this was especially surprising because of the fact that these are conserved fields. And really, the mechanism that drives the traveling states are kind of very similar between this situation and the situation of the Vichek model where there is no conservation law. But the kinetics of coarsening is very different. And understanding the kinetic of coarsening, especially in the case of the conserved fields, is very much still an open question. OK, I'm probably going way too slowly, but any questions about this? Yes?
Is the passive molecule not affected also by the density? So if you increase the density, you're going to get more waves?
You mean No, the waves are not affected by the mean density. So what I need to get these waves is the fact that I have to have some mechanism for forming a static pattern. In this case, it's this phase separation. And then I have to have the non-reciprocal interactions. But the density per se doesn't really come in. Although, okay, if you have too low a density, you're not going to get the phase separation to begin with, which is what you need. So, okay. Okay, I was hoping to tell you also a little bit about these pneumatic systems, okay? And just a very quick reminder, what is a pneumatic liquid crystal? Well, a passive pneumatic liquid crystal is a fluid of rod-like molecule that, as you either increase the density or lower the temperature, can go from a state which is isotropic, the molecule pointing in random direction, to a state that is still a fluid, is still a liquid, but on average the molecules are oriented in the same direction. And the direction of broken symmetry is identified by this unit vector called the director, which is often drawn as a vector, but really should be thought as a two-headed vector. So the order parameter for pneumatic order cannot be a vector because of the up-down or n minus n symmetry of the system, but is a tensor, a rank 2 tensor, known as the Q tensor. And so S is the magnitude of the pneumatic order, and N is this director field. That's a regular pneumatic liquid crystal, was used for, say, all our displays. Or in active pneumatic is when your rod-like molecules actually are active particles that may be shake back and forth or exert force dipoles on their environments. And as a result, generate this type of self-sustained, relatively chaotic or turbulent-like motion. This is Myxobacteria, is a bacterium. These are experiments from the lab of Josh Shevitz at Princeton. And the color is the mean orientation of the bacteria, so you see large regions of alignment, large regions of pneumatic order. And the reason pneumatic order in active matter is interesting is because over the years, it has been seen in many, many systems, and sometimes was actually surprising. Sort of the paradigmatic system is this first one on the left, which is a fluid made of protein extracted from the cell cytoskeleton. Long filaments, long polymers called microtubules that are fairly stiff polymers, cross-linked by a motor protein called kinesin, actually by clusters of kinesins, that essentially they can walk on the microtubules. The microtubules themselves are polar, and when microtubules of opposite polarity are cross-linked by this motor protein, their walking essentially displace the bundles of microtubules relative to each other, and the bundles is your active units that exert force on the environment, as kind of shown in this cartoon. And the result are this self-sustained, turbulent-like motion in a system that is actually a zero Reynolds number, but that's kind of another story. And the telltale signature of pneumatic order are the strong distortions that these arrows point to, which are the topological defects of a line field, as opposed to a vector field. We'll come back to that in a minute. So this type of pneumatic order has been seen, for instance, in vertically vibrated grains of rods, in cell sheets of cells that just go back and forth. Hard to see here, but when you image it and follow the cells, you see the pneumatic order. And even on the scale of entire organisms, this is a freshwater polyp called Hydra, and what you see here is pneumatic order of supracellular fibers, muscle-type fibers of actin that span the cell body. And what is interesting about these systems is are these topological defects. So what you have here, topological defects, well, orientational order, or any kind of order, is interrupted by topological defects also in equilibrium. And the structure of the lowest energy topological defects is a fingerprint or a signature of the broken symmetry. the lowest energy topological defects in a vector field are asters or vortices. But the lowest order topological defects in a line field, which is the nematic, these are called disclinations and carry a topological charge which is plus or minus 1f. The topological charge is defined by the angle through which the order parameter winds when you go around the core of the defect, when you circle the core of the defect. And you find plus and minus 1f disclinations on your fingerprints if you look carefully. Now, in equilibrium, it's well known that we have a very well-developed theory of phase transition in 2 dimensions based on defect unbundling, the Kosterlitz-Thouless theory, because we can map topological defects onto essentially Coulomb charges, and opposite sign defects attract essentially with a Coulomb interaction of strength controlled by the stiffness of the nematic liquid crystal. So you might have topological defects if you quench your system down from high temperature, but then the system coarsens, topological defects annihilate, and you get an ordered state. In the active nematic, topological defects are continuously generated by activity, and furthermore, if you follow these arrows, it really looks like the triangular shaped minus 1f and the comet shaped plus 1f are actually repelling. They're moving away from each other. So defects become motile, they are spontaneously generated, and they're really key in driving this, and it looks like they're repelling, okay? And they're really key in driving these self-sustained turbulent-like flows. So what we, these flows, by the way, are driven by what we call active stresses. As I said, these bundles of microtubules are shifted, they sort of extend, and they exert forced dipoles on their surroundings. And so you can see that the active stress will depend on the orientation of the filaments and be proportional to actually the nematic order parameter with a strength that is known activity that actually depends, in the experiment, it will depend on how many kinesin you might have in your system, or on the concentration of ATP, which is sort of the fuel that these kinesin motors use to do their work. And this alpha, which is we call activity, can be negative for this situation where the dipolar forces point out. There are also systems in which it's positive, like in muscles, where the forces tend to be contractile. But here I'm focusing on this situation. So how can we understand these dynamics and the motion of the defects? Well, one simple way relatively simple way to do this is to construct a continuum model, essentially a field theory, hydrodynamic equations, which we will write we describe our system in terms of the flow velocity and this orientational order parameter, for which in equilibrium we know how to write down a free energy. This is sort of in 2 dimensions, the transition in mean field is continuous, so we have a q square and a q to the 4th term, our double well potential, and a nematic stiffness that controls the interfaces between normal and nematic, or isotropic and nematic regions, with a characteristic length scale that actually determines the core of the defects. So this is the small scale in our problem. The dynamics of the orientation of the Q tensor is controlled by relaxation with this free energy and coupling to flow, because shear gradients or vorticity clearly can turn the filaments, so they can distort the orientation. And this is true in conventional passive nematic liquid crystal. There is this key coupling between orientation and flow that drives the dynamics. The other equation we need is sort of in principle, an equation for the flow velocity, in principle, a Navier-Stokes equation, but these are actually fluid layer on a substrate, so we have friction, and inertia is negligible, so we just balance forces into a Stokes equation, which balances friction with pressure gradients, viscous stresses, and our active stress, and elastic stresses that have to do with energy cost for deforming the orientation. So the only term that is active here is this active stress. And actually, the balance between elastic stress and active stress defines a length scale, which is controlled by the square root of the stiffness divided by this activity, which turns out to be the length scale that controls essentially the mean separation between the topological defects. And this has been actually, this kind of scaling has been verified in experiments. Now, if we simulate these hydrodynamic equations on a computer, we actually reproduce the dynamics seen in the experiments. This image to the left, the color is the degree of orientational order, and the segments are the director field, so it's the alignment. As you see, defects are generated in these regions of disorder. They unbind, they move around, they recombine. This image to the right, the color is the vorticity, and the arrows are the flow velocity. So we have counter-rotating vortices, and the defects generally unbind in the high shear stress region between counter-rotating vortices. And you can actually calculate a lot of things. You can calculate the mean vortex size, the mean defect separation, that are both controlled by this active length. And you can convince yourself that there is kind of a mapping, in quotation, between the dynamics of the vortices and the dynamics of the defects. And so it becomes tempting to actually try to describe these dynamics by focusing on the dynamics of the defects and construct a non-equilibrium version of Koster-Ristauler's theory for these motile charges, which is something we have done, and if somebody is interested, I can tell them more about. But why are the defects motile? Well, it's actually very easy to understand why the defects motile. So the deformations of, so here I've written a simplified version of the Stokes equation where I have dropped many terms. I've only kept the friction, viscous dissipation, and these active stresses. And it's clear that the active stress can be thought of as a source for flow. So this equation says that deformations of the orientational order generate flow. So I can do a simple calculation. I can actually put in here the Q configuration corresponding to specific defect structure. And I can actually calculate the flow that distortion generates, so the defect itself generates. For a plus 1F defect, which has this comet-shaped object, these thin white lines, it generates two counter-rotating vortices, and due to the symmetry of the defect, the flow will be non-zero at the core of the defect. And so this defect essentially behaves like a colloidal particle. It rides along with the flow itself, it itself generates. The minus 1F, well, generates actually even more complicated flow, but by symmetry, the flow has to be zero at the core, and so this is not a motile particle. And more importantly, the direction, so the plus 1F becomes like a polar self-propelled particle, like my fish or bacteria, if you like. And the direction in which it moves is controlled by the sign of activity. In extensile system, plus 1F defects move towards their head. In contractile, they move towards their tail. So the direction of motion of the plus 1F defects is actually tells you about the nature of the active stresses. And this has actually been used. For instance, the direction of motion of plus 1F defect in epithelia was quite surprising because it revealed the presence of extensile stresses in systems that are contractile at the single cell level, and this is something that is still not completely understood. I would like to tell you one more quick thing. I just have a minute. So we've done a lot of work on this defect dynamics, but the one quick thing I would like to tell you is we have this turbulent-like flow, and it has become one subject of a lot of research lately has become, can we actually control these flows? Can we tune them? Can we do something useful with them? And our suggestion is that we can do that by controlling the dynamics of the defects. And so the question we've been asking is, can we actually design, so activity, this parameter alpha for now was homogeneous, but it's possible through using optogenetically modified protein to actually create patterns of activity in space and time in these kind of systems. So can we design activity patterns that will control the defects and allow us to generate the desired flows? Well, so this is what's done actually mostly by Suraj Shankar and a very talented undergraduate actually in Santa Barbara, Luca Scharrer, who is now at the University of Chicago. And what we did is to exploit the linearity of the Stokes equation to construct an approach for doing what I just said. So here is the Stokes equation rewritten in a slightly different way, viscous stresses, friction, viscous stresses, friction, I divided out the friction, active stresses with possibly especially inhomogeneous activity, and pressure gradient. The defect velocity is determined from solving this equation and then calculating the mean angular average defect or vorticity. Defects can also rotate. Now, the structure of the flow clearly is determined by the combined symmetry of the activity pattern and the Q tensor, the nematic texture. And you can characterize each one. The symmetry of the Q tensor of the defects can be characterized by their topological charge, or equivalently by what we call a symmetry number. You can translate things in the complex notation, and then the plus 1f will be described by this kind of quantity, and so as a symmetry number of 1, the minus 1f is a symmetry number of 3. The activity profile can be decomposed in angular Fourier basis in 2 dimensions. And by inserting this here and then asking which kind of flows you can generate, you can actually construct sort of a selection rule for the kind of flow that each structure of defects and activity will generate that allows you to tell, so for instance, a constant activity will give motion of the plus 1f but not of the minus 1f. A gradient, linear gradient of activity will give you rotation of the plus 1f and no motion for the minus 1f, and so on. We really have a selection rule based on the difference between the symmetry number of the defect and the polar angular component of the activity. And only these values will give you a defect velocity or a defect vorticity. And so this is going to be my last slide. By using these, we construct activity patterns that allows us, we call them topological tweezers, that allows us to grab defects and move them around. And for instance, here we are actually generating 2 defect pairs, and we are braiding them around each other in this trajectory, which is also generate well-defined motion. And there have been actually experiments measuring defect trajectories and their braiding, and arguing that the braiding in this turbulent dynamical state that these fluids exhibits provides a quantitative measure of fluid mixing. So this goes along with our idea that we can map flows and defect dynamics. And we are hoping to kind of use that experimentalists may actually be able to use this to kind of generate the kind of dynamics they want. And actually, there have been work along this line by Matt Thompson at Caltech, who has actually used something like activity patterns to move around and generate precise structure. So I probably spoke for too long. I am not going to go through this. I just want to tell you that in this hydra, which is an organism that regenerates itself, it has been shown experimentally that topological defects actually are associated with specific morphogenetic processes during regeneration, such as the location of the head, the foot, the tentacles, and we are working on understanding that. But I'm not going to go through that. So just to conclude, I try to convince you that there is a lot of new physics coming from cell propulsion. Active particles can organize when passive ones will not. Active fluids flow without externally applied forces and perhaps can be harnessed and controlled to produce coherent motion. Currently, very active area of research is try to quantify the work and heat generated or used up in active systems, sort of to, again, be able to control them and so on. And I just want to thank you, and this is a photo from my group and a list of people who did a lot of the work I talked about. So thank you again. I hope there are some questions.
Questions? It's a conceptual question. You know, like what you're showing us is that from the theory perspective, you can always like engage in simulations and predict, quite a wide range of behavior. So I'm curious in general, how often is the theory ahead of the experiment, and how often is the experiment ahead of the theory? I mean, like trying to understand how the back and forth.
So it's interesting. I think in this field, it started out as a theory. For many years, it was really theory-driven. Partly because, although in principle, these ideas were supposed to be able to be applied to living systems, there was no way for testing them in any quantitative way. And eventually, people started making these more controlled experiments, like the Dogic experiment or these active colloids and so on. And now, I would say they're kind of, now I think there are experiments are driving the theory. For instance, I'll give you an example. One of the things that Zami Dogic is working on right now a lot is phase separation of active liquid crystal and the passive fluid, the property of interfaces, and wetting behavior. And this is really not understood theoretically. I mean, I've done some work on this, but the honest truth is this is not understood theoretically. These active fluids, when they phase separate, they're these active liquid crystals. When they phase separate, they're heavier than the passive fluids, so go to the bottom, and they climb the walls of the container. And they can undergo complete wetting surrounding the passive fluid. And this is not understood at all. So now we are inverted a little. But the other thing is that there has also been quite a lot of concrete progress in applying these models, better versions of what I try to sketch here, to biological systems. For instance, you probably know about this, but Boris Schreman and Sebastian Strachan have actually shown that what I call the active stress, which is in development of the fruit fly, is related to myosin, nematic order of myosin, does generate the flaws in the early stages of the development. And they measured these two things separately. They were able to show that they're connected by this kind of dynamics. So thank you for the question.
David?
Yeah, I have a question on the first part of your talk. So you showed us that there are systematic ways to go from particle descriptions to fields, to use those field theories to predict phase diagrams at a mean field level. And it's known, at least in passive systems, that mean field phase diagrams are usually not that accurate. You know, they will predict, underestimate critical points, get qualitatively or quantitatively incorrect exponents. So I'm curious to what extent there is development beyond mean field theories. Can one do systematically better, or what is it that explains the success of mean field theories?
No, there has been a lot of development driven largely by Cates and collaborators to go beyond what I showed you here. For instance, there are in this, I said that you can map this on a Calmi-Hilliard type model, but actually the reality is that there are other terms that you will obtain that explicitly break time reversal symmetry, meaning they're not allowed in equilibrium system. And although there is still a little bit of controversy, for instance, it seems some of these terms can actually provide, arrest the phase separation, provide line scale, provide finite size clusters and things like that. The changes to the, say, coexistence line are very small, okay? But there are qualitative changes to the kinetics of the phase separation. And yes, I swept a lot of the stuff under the rug, yes. And actually also, my case has been also using sort of G-type methods to study the systems and things like that.
Yeah, that's exactly.
Yes. I think there was a question up there.
Yeah, I have a question on the first part of your talk. I know you treated your particle, but does it not indicate
Oh yeah, people have been studying cell-propelled polymers. Now you can self-propel them in many ways. You could, for instance, say only the head, imagine your polymer as a bit of particle connected in some, a string of particles connected in some way. You could have propulsion only on maybe the head particle, or you can have propulsion on each particle, and things get, and then, so yes, there has been quite a bit of work on this. These days, people are just making almost anything self-propelled, and sometimes you learn useful stuff, sometimes maybe not so much, but to be honest.
Maybe a question for me. So going away from self-propulsion, so if you do the second part, the nematic, just you introduce activity just by division, growth and division. Do you expect exactly the same?
So division produces extensile stresses sort of similar to the ones I was talking about here. So at the continuum level is not all that different, although then you don't have, so my flows were always incompressible, density constant, so then you don't have number conservation.
Right.
And actually, we are looking at what we now call compressible systems where the density can vary, partly because of these, the experiments with spatially varying activity, then actually particles will accumulate in a region, so you do need to incorporate. So there are some similarities, but there are some differences. Yeah. By the way, I should also have said that in this self-particle model, the ABPs that I introduced, there has been actually a lot of work on understanding properties like the pressure of these particles, the surface tension, including by here, and many other people. And but understanding the same kind of mechanical properties in systems where there is flow, like this pneumatic, is completely, there's really nothing at all yet.
Yeah. What does the process look like in these, to go from the proposed field theory to prediction to validation? And what's the prediction of a field theory?
I don't know. So, okay, here one of the, well, I don't know if they could call it a prediction, but one of the, it was this motion of the defects, and the fact that, for instance, both the mean separation of the defects and if you actually look at the flow, there is all this vertical flow is really like a turbulent kind of dynamics. And you can make predictions on the scaling of these line scales with stiffness of the pneumatic or activity. And these things have been measured in experiments and verified to scale in the same way as predicted by the theory, for instance. Or look at the spectrum of energy, which energy is transduced for small to large scale or vice versa. What is really not known yet, so in the theory we have this activity, alpha. In the experiments they have the concentration of kinesin and maybe of ATP. How do we map the theoretical, so the quantitative mapping of the theoretical parameters with experimental quantities, that's still not understood.
All right. Maybe we leave the rest for offline discussion here. So, but in the end, let's thank Professor Marchetti.